So I'd like to introduce Jake Veilleux. I've known Jake for 15 years, 10 years, something like that. Jake's got a big background in aerospace, standard part modelling, just standards in general. He now is a co-founder of Veilleux with me. Quick marketing pitch there, and I'll let Jake take it from here.
Thanks, Mark. And Pascal, always good to see you too.
Same with you.
So, good morning, everybody. Today my objective is to provide a high-level overview of standard part, master model, and design table creation. Touching on standard part modeling best practices, some important functions within component families, and compatibility with part catalogs at the end. Then I'd like to discuss how we can take a standard master model, integrate Yoke features that can lead to a serious reduction in design and manufacturing errors, leading to better production quality in our assemblies. So what I'm going to be showing today is kind of a product of what I have experienced throughout my career, as well as what many of my colleagues have experienced. So in the spirit of the Code Conference, please feel free to interject in anything that you have done if you work with standard hardware at your company, or if you have any questions throughout. I would love to see this be a catalyst for everybody to go and start bringing their fastener libraries into the 21st century. So I'm going to kind of move on here with posing a question. There we go. So what's wrong with this picture? All right, we've got a little block with a couple countersunk screws, some washers, some nuts. Take a mental screenshot of this because we're going to come back to this in a little while. So some impacts of a bad fastener ecosystem. So these are some stats that I found while scouring my Uncle Google, and I'm sure that many of you will look at these numbers and kind of shake your head and understand this pain that you have felt yourself. So about 15 to 25% of all engineering change orders and mechanical assemblies are fastener related. About 20% of manufacturing rework cost is from fastener selection and implementation. So if you look at the cost multiplier effect, say if you have a fastener slot that equates to 50 cents, by the time you actually go back, have the engineering changed, it goes through change management, it goes through planning, it gets to the shop floor, that quickly compounds into a very, very large amount of money. So companies that go through a fastener standardization process and have a robust selection process in place have shown to have 40 to 60% reduction in fastener related reworks typically associated with fasteners. So today I want to focus mostly on mechanical fasteners. What we're going to talk about today can easily apply to electrical connectors, company part families, what have you. Fasteners are typically an out-of-sight, out-of-mind component. Most people will just check to make sure that they're there and not really do a deep dive to look at thread class, fastener length, any other attributes that may be affecting that assembly. So it's easy to get stuck as an engineer in the big picture and forget about the little things, right? The devil is always in the details. And fasteners in that respect are the bottom of the totem pole, which is kind of fitting because they're the foundation of everything that we are literally producing for our customers. So they deserve a lot more critical focus than we tend to give them. So it always comes down to little things. That being said, I'd like to share a quote with you from a very popular businessman who made a big splash in the mid-1990s. So you can't argue with little things. It's little things that make up life. No Simpsons fans? Okay, well that one's just for you, Dad.
Thanks, Jake.
All right. So how do we end up in this kind of situation? Well, we live in a time where we have an access every day to an infinite amount of information. And it is so easy to go out and find what you're looking for. So here I've got 4 models of the same part number, AN4-5. So AN4 is a very popular fastener family used in Army and Navy situations as well as general aviation. So it doesn't take a rocket surgeon to look at these 4 and see we have some problems. So, just pointing out a couple of them, our origins are located in different places. places. And you can look and see at the our little compasses here, they're even modeled in different orientations. Geometrically, they're off. We've got different head sizes. We have the overall length of the fastener, length of the threads, they're all varied. We have no delineation on one where the threads end and the shank begins. All of these become problematic. All of these contribute to those percentages that we were talking about just a minute ago. So one big thing here is threads. We've all got that one hotshot engineer who likes to show his CAD modeling prowess and fully define a model. But putting threads onto a standard part is actually pretty problematic. You don't think about it, but the amount of B-rep that you are adding to that fastener is quite substantial. So when you start talking about larger and larger assemblies, those threads are still visualized. So it can actually put a real drag on your performance from your graphics card. So threads are cool, but you don't want to have threads. So, and it doesn't have to end here. You know, you have, of course, McMaster Carr, Carr Lane, GrabCAD, Uncle Joey's standardmodels.org. You can find the information anywhere. You can even pull it from a vendor-supplied model that you got from a separate component and save it. So we're going to toss all that out the window, and we're going to go through a clean sheet example of how I prefer to set up master models and design tables, merge them into a component family, and then publish out these selected fasteners that we want the engineers to use in our designs. So for this example here, we're going to use MS-24693. So this is a countersunk screw, very commonly used in military applications, general aviation, consumer electronics, and even in the jewelry industry. So it's a very, very popular fastener family. I always like to start with an industry standard because the parts are 100% defined. Every dimension you have, every physical attribute, it is defined. All the materials that the fasteners can be made from, the available finishes for each of those materials, as well as notes concerning the recess, the options that are available there. There's just a cornucopia of information for nerds like me. So let's walk through the process of creating a design table. So I know none of you have heard or seen anything about Excel at all this week. But when you're creating a design table, it's good to take your information and separate it into three big chunks. So number one, and this one's very important because if you don't have it, CATIA is going to yell at you. So you have to have a part number column to actually integrate a design table into a part. If it's not there, CATIA is going to scream and make you do it. So the second group is your engineering attributes. So these are all the high-level attributes that you would pull from your spec to help you identify a specific configuration of that part. It can be your material, your thread class, what kind of head you have, whether it's a cruciform recess, a dovetail, flathead, socket head, so be it. Things like pitch, and all of those things. These are typically the attributes that you are going to assemble to create the part number for that particular configuration. So this is a very long design table. So this is the same you saw on the previous slide, just slid a little bit to the right. So after our engineering attributes, we have our design attributes. This is everything that's actually going to drive the 3D model of your part. So your industry standards will typically give you a range, a minimum, a maximum, an absolute minimum, or an absolute maximum. So all of that information goes into the design table. So typically when given a range, I like to model based off of the nominal dimensions. So I'll still put the minimum and the maximum into a design table, and I'll calculate the average because it's still good information that we will later put into our tree for anybody who needs to review that at some point.
Do you consider the dimensions that are not in your design attributes to be sort of fixed, like the head angle at 100 degrees?
Yes. Yeah, so anything that's going to change from one configuration to the next goes into the design table. There are dimensions that are going to be constant because it's not, you have the angle for the head, but also the radius between the shank and the head. That's typically going to be standard as well. So all of those are just attributes that are in the model only. So when I'm creating a design table, I like to start at the top of the spec, and that's typically your smallest thread size that's on there. I'll start with the smallest size and the very first dash number that's in that specification. So from there, we have multiple materials that may be available. So you may have that first part number that could be made from steel, it could be made from aluminum, it could be made from brass. So each of those materials needs to be accounted for as a specific line item in the design table. And then compounding on that, you have different finishes that are available for each of those materials. So you may have several types of passivation for stainless steel. You may have 2 or 3 options for anodization for an aluminum fastener. Of course, capping and plating for regular steel, all very popular. And then you may have other attributes like drill threads for a cotter pin, drilled head for some safety wire. So all of that starts to build up where for that one part number, you end up with a block of potential combinations between materials, finishes, and so on. So once you have that one block, you can take that block and you can reuse it over and over for subsequent dash numbers and for subsequent threads within that part class. So once you have that initial block done, it becomes very easy to populate out the rest of the data. So there's more than one way to skin a cat. There are millions of ways, I'm sure, to create an Excel design table. Copy and paste is always a good one, but I utilize a lot of formulas like VLOOKUP, concatenation to assemble my part numbers. So you can get really creative, and you can have some very, very complex design tables that have thousands upon thousands of configurations that you can put together in an hour or two, perhaps even quicker if you're really good at whiz at Excel. All right, so actually creating a master model. So when we open up a fresh part, we go to the tools ribbon, and we have our Excel spreadsheet icon that we can attach to this design table function. So it's going to open up this dialog window, and we have a couple of things that we need to address. Of course, we want to name it. I like to name it the name of the specification that I'm dealing with. And we have 2 options. We can create a design table from a pre-existing file, or we can create a design table with the current parameters in the model. So that being said, you can start by creating an Excel file for your design table, or you can start with a model that has all of the parameters created in the tree, and you can take those parameters and write them to a design table where you can then go forth and add your different configurations. So I like to go the route that I just showed you, because most of the specs that I deal with have thousands upon thousands of configurations, and it's easier to just create that data and push it into the 3D model versus the other way around. So number 5 there, so vertical or horizontal. So you can set up your design tables in 2 ways. So a vertical design table is where all your configurations are stacked vertically. So each row represents a different part number configuration from that spec. And conversely, a horizontal is the opposite. Each column would represent a new configuration of that part. So either way is fine, and different contexts of parts may point you one way towards the other, but what I had just shown you was a vertical design table. And down here at the destination, so it's not shown here yet, but you can actually select where in the tree, which bucket you want your design table to go into. So if you've built up a relational set that has different buckets for things like formulas, rules, reactions, what have you, you can create something for design tables and direct the system to put the design table there. Otherwise, you have to go through the process of right-clicking, reordering. It's a neat little feature they put in there. So here's where the magic kind of starts to come in. Once you have clicked OK, you get this dialog box that's here in yellow. You can see in the center, every column that I have in my design table is shown in that columns tab. So we have the ability, like I said, where we can create parameters in the tree for everything that is in our design table. So when you hit create parameters, you get this secondary box, and everything comes highlighted by default. So we're going to push everything over, which is fine. But if you're in a situation where you only want to expose certain parameters, you can multi-select what you want to have go into the model, and it will only create parameters for those. So you can see there's one massive data dump of parameters into the tree, and once that is done, you can see where on the table over here on the side, it shows the parameter in the tree and what it is associated to in the design table. So for whatever reason, you have somebody from your checking group or whatever say, this has to be all capitalized. you can go in and you can modify your parameters to show that they're all capitalized. And it will still show that even though your part number is all capitalized, for instance, it is still associated to the part number column in your design table. So from a modeling perspective, this is where we need to make some good decisions on how we want our CAD to behave in 3D. So where we put the origin is very important. So I put the origin, and let me rephrase that. We should all put the origin at the fastener's point of interface to logically where it's going to be assembled. So if it's a bolt, you would want to have the origin at the base of the flange of the bolt. For a countersunk fastener, you want that to be at the top face of the countersunk bolt. So how that works, if you're making a design change in design, and you go from a countersunk hole and you decide you want to have a hex head bolt, you can swap one for the other, but because the origins are located consistently, you're not going to have to readjust that part's position in space. And then Z should be normal to the direction of orientation. So it doesn't, and if you follow that process throughout all of your master model and design table creations, you are going to have a fastener library that is going to flow from one to the next very, very easily. So when we have,
we went through this exercise probably about a year ago. Frantically trying to create a CATIA library for parts, and I was trying to find call it an industry standard of orientation and origin. Origin, totally agree with you. The point of interface, and also orientation. Z-axis is your parallel to the axis of the fastener. I couldn't find anything to define that industry standard. We all agree, yes, like verbally.
I don't know that one exists, to be honest.
So I was going to ask you, when it comes to agree on Z-axis orientation, but positive or negative, or is the fastener in this case is that the V direction right there? Is
That would be your positive Z, yes.
Okay. So I guess you can go either way, right? You can negative Z.
The name of the game here is consistency.
Yes.
So even what we were showing in that second slide where you've got everything in the center, consistency is key. And if you structure your data to a point, even if they're all over the place, if you have constructed a joint in a way where say your master axis system, they're all named the same, as long as, even if things are all over the place, as long as those names are the same and you update a assembly with a new fastener, the engineering connections will automatically update based off of those publication names. So even if it's not ideal, but as long as it's structured in a way where you have consistent naming, things will move to where you're not having to go snap stuff into place. But it's just easier to have them consistent across the board.
I might suggest that because there seems to be a lack of industry standard, it's an open opportunity to do something similar to the Jeeves Smith scale, parametricness.
No, that might be a great opportunity to go, put out, my words aren't working, caffeine's wearing off. Maybe some kind of a white paper, just discussing best modeling practices for standard hardware. Because it's something that when you think about it, it should be common sense, but it's not. We've looked at some of those examples.
But you can't get SolidWorks and CATIA to agree on the Z interface.
I can't speak to Solid. I have a little bit of undergraduate experience with SolidWorks, but so pretty much all of my professional experience has been in CATIA. But no, that's a good point, and maybe that's something we can talk about at some point in the future. So from an modeling perspective, so as we start to this master model, we want to associate all of these dimensions back to our design table. So we want to make sure that when we're creating dimensions, we want to create a formula that ties those to our parameter, because our parameter is associated to our design table. So as we go from one configuration to the next, the part is following the bouncing ball, and everything will dynamically update to the next configuration in the model. So it's good to kind of separate your tree out into your positive elements and your negative elements. So positive elements represent the body of your fastener. And what I've got here is me starting to create the Boolean remove plug. It's going to represent the cruciform recess for this fastener. So it's good housekeeping, but as you go and you start trying to test and try to figure out where your bugs are, it makes it easier to kind of figure out where the issues are when you have two distinct areas of the model. So we kind of end up where we have a basic master model definition. So I've got everything, my parameter set is separated, like we were discussing with the design table, my engineering parameters, and then one for my design parameters. I do have some subfolders within my relational set, so I can group together all of my formulas, design tables, rules, reactions, and any other information you want to add. Of course, our part body is separated into our positive and negative attributes. So we have a nice, compact, clean tree. And once you have that, you can go back to the model, you can double click on your design table, and it will show you all of the available configurations of your tree. You can go through and you can select on various ones, hit the apply button, and you can watch the model morph in front of you. So now that we have a model together, now it's time to test it out, see if we found any issues. So we're going to start with creating a component family. So in your apps, we want to go for the component family definition. And similar to the design table, you're going to get a window that pops up asking you for a name and description. And again, I use the name of the standard specification, specifications title, and it creates us this component family. So the way this is structured is actually pretty nice. So you can see in the top left in the green box, it actually has our master model and design table loaded into the component family. We've got maturity mode. So this one's kind of important. So I have this set to manual. The default is set to automatic. So why is that important? So in automatic mode, you resolve a part and the part is automatically released. In manual mode, it is resolved to input. So I recommend staying with manual mode as you are testing out your part family to see if there's any kind of issues. Deformability mode. So I'm not going to talk about this today. I'm actually going to include this in a webinar in the middle of next month. But this is actually some really cool functionality. So this is a rigid component. So it's defined as rigid. But we also have a deformable part. So that is a part that you can have multiple instances of in your tree shown in a different configuration. So think of a spring that is compressed in this situation, compressed more in this situation, or a zip tie that you have in varying diameters throughout your model. So that's where the deformability comes in. Very cool. Filters we'll touch on. Oh my gosh. That was crazy. Sorry about that. Filters and where used, we'll go over in a minute as well. So in the little purple boxes, all of these are the possible configurations that come from the design table. And for MS-24693, there are 2,310 possible combinations of lengths, materials, finishes, etc. That's a lot, but it's not the most. You get into specifications like AN3 through 20, where you have 19,000 possible combinations. NAS 1149, washers. That is got a very large number of materials, finishes. You have the options to enlarge the center hole of the washer. That is just over 17,000. So you can deal with a tremendous amount of data when you're putting these together. So, first thing I want to do, once I've created my part family, is I want to go through and I want to test my models. So if we go to the test and resolve family items, which is the two bolts next to each other upside down, we get this dialog box that shows up. So do not make, well no, I'll wait for that one. Let the suspense build up. So what we're going to do here is, hindsight's always 20/20. We are going to go and we're going to select test items. Once we hit test items and we hit execute, behind the scenes, Katia is going to go through and it's going to virtually resolve each component in that design table. And either it's going to work or it's not going to work. So if we look at this column, the second column in the tree here, you have item number 3. We have an X and we have a check mark. Check mark means the part resolved and updated. The X means the part did not update. So, we've made a mistake. We need to go back to our model. We have to understand what's going on. So in this particular instance, I noticed something kind of odd. There's actually a pretty specific cadence to this pass-fail. We have a fail, pass, pass, fail, pass, pass, fail, and that pattern was kind of followed for quite a bit. So I made a mistake. So with this particular standard, there is a note that for fasteners that are 2 inches in length, or up to 2 inches in length, the threads will extend up to within 2 threads of the bearing surface. So we know we have up to 2 threads that will be shown as incomplete. So when I structured my master model using the pitch information from the design table, I actually have that calculated out based off of the different families. And that's on the right hand side, you can kind of see how that is. You have the 0.036, that represents the maximum number of incomplete threads, and then your 0.156 is the total length of the fastener. So if you look at the sketch in the center, those curves are self-intersecting, and that should not be right. So hindsight's 20/20. I should have taken a picture of this for the presentation, but I had made a mistake filling out my design table where a couple of my length attributes were left blank. And so when I reused my block of information with the materials and the finishes, that was repeated over and over again. So when you're creating a design table and you have a blank space, CATIA is going to automatically maintain the previous value. So as I was resolving, it was maintaining the previous value, which was bigger than the overall length of the fastener. So I was getting that self-intersecting curve. So, but that's why we do this. You know, we're trying to force out all of the issues. So I made the fix, went through and retested all green check marks, which is fun, which is great. So now we have a very generic master model and design table, but we can do better. It's 2025. So what are some things that are important to our organizations? What are things that we check for that are important to manufacturing, design integrity? You know, consistent origin orientation scheme, mechanical interfaces. You know, maybe we want to add a center line or an axis system for constraints. These are also very important for when you want to move into more parametric modeling in the future, KBE. So we've got other mechanical securing elements I was mentioning earlier, like drilled threads and drilled head. Material reference elements. This is kind of like a cherry on top type of thing, but a lot of bolt standards will actually give you different shapes and patterns that are present on the bolt of the head to give you an indication of what the material is that the bolt is made of. We want to know maybe usable threads, incomplete threads, fastener pitch, edge distance. And we want to make sure that you know, we're putting the right size fasteners in the right size you know, nuts, nut plates, potted inserts, all of those together. So how's it doing that? It's a mind of its own. So what can that look like? So one of my favorites is probably the easiest and has the biggest bang for the buck is color coding your fasteners. What do I mean by that? Well, if you're putting a 1032 screw into a part, you want to have a 1032 washer, you want to have a number 10 nut. Everything 1032 should be the same color. So where you can very quickly look at it and say, they're all the same color, they're all matching thread class, we're good, let's move on. Whereas if you have a 1032 bolt and somebody accidentally put an 832 nut on there, you have a color mismatch. Very easy, very high level. So creating surfaces and sewing them onto the part body to define the threads on your part. So we mentioned the usable threads versus unusable threads or incomplete threads. So what you see there in white would represent the available usable threads, and that yellow band on top is the usable threads based off of what's on the standard. And we can calculate all of that because we know what our pitch is, and we can create that reference element and put it onto the model. So of course the mechanical interfaces we were talking about earlier, an axis system, center line, and thread engagement. So coming from an aerospace background, this is something that's very important. Because when you have fasteners that are too long, over tens of thousands or hundreds of thousands of uses, you're starting to add a lot of unnecessary weight to the aircraft. So let's say, for instance, you have 1.5 to 3 threads past the end of a nut, where a locking feature is your company standard. Again, we know what the pitch is. We have that attribute from our design table. We can calculate that and put a reference element onto our fastener. So when we're looking at the fastening joint in 3D, as long as the end of the nut or the locking feature is somewhere within that band, we can quickly tell that we've met the requirement. So with that, we kind of have to go back to our design table, right? Because these elements are going to dynamically update as we go from size to size. Our color's going to change, our picture's going to change. So we can add on to our design table when we start to put in our specialty attributes. So here I've got RGB colors for my color control. And it doesn't have to stop there. You can also add in other specialty attributes. They could be maybe Innovia specific attributes, like is this a program specific fastener? Does it have an effectivity, depending on what your needs are. All of that can be put into the design table as well and furnished into your part. So what does that get us? Can you kind of see the direction we're going in here? So I mentioned in the previous slide, pinch and edge distance. That's what you see here, these surface elements. So say you have a requirement where your fastener pitch needs to be 4 times the diameter. Well, that could be the outer surface representation. And say you have a 2D plus 065 requirement for your edge distance. That's the narrower band that's on the inside. So how do we benefit from this? How many of you remember that little picture I showed you in the very beginning? So what's wrong with this picture? Now we can kind of quickly get an idea. So for starters, I don't know how well you can see it on the screen here, but I've got a different color fastener than I do a nut. Well, geez, I can look at this a little bit closer. I've got an 832 screw with an 836 nut. So I've got a coarse fastener with a fine thread nut. We can't assemble that. That's a problem. We can look at the picture here where we can see that we've got our fastener pitch elements intersecting with each other. So we're violating our minimum pitch requirements. And we're just barely not meeting our edge distance requirement in the bolt on the side. So all that at a quick glance versus what we looked at before. Not to mention, if we look at the one on the left here, you can see that our fastener element for the thread engagement is sticking out beyond the end of the nut. So we have an opportunity to reduce the length of that fastener by 1 or 2 pitches to get within the requirements. So there's a lot of benefit to this, where you don't have to wait until something gets all the way down to the manufacturing floor for it to become problematic. You can pull it up front to where designers, checkers can very quickly review these requirements, fix the issues, and move on. So the amount, we did this in a previous life at Gulfstream, and it made a massive impact on reworks from the shop. So now we've created all of this, how do we get our designers to use this hardware? So we're back at our component family. I've changed my maturity mode to automatic. So as we resolve these parts, they will automatically release. So we're back into our test and resolve family menu here. And this is where I said, heed my words, be very careful here, or you will lock up your machine for a very long time. So we have all, and we have selection. Has anybody worked with master models and design tables in V5 by any chance? Okay, so resolving parts in V5 is very fast. You can do several thousand parts in an hour or 2, but that is a file to a directory. We are now dealing with servers, and the amount of time is unfortunately much higher to resolve these parts. So if you want to resolve everything in your library, that's fine, but be prepared for it to take time. So for the sakes of this presentation, I'm just going to go based off of selection, creating some filters, and going that route. So I've selected, just for the sake of the explanation here, these first 6 fasteners. So selection, we're going to resolve these parts. So batch resolve, if you do have a larger number that you want to resolve, you can select that. Resolve items will lock up your session, so you won't be able to do anything else. But if you hit batch resolve, you can actually navigate between tabs. You can continue working, and it will do the resolution in the background. So that's really the better way to go, unless this is sort of a lights out type thing where you don't care either way. Yeah.
Some of the last slide, where you can see it there, those surfaces.
Mm-hmm.
Is that strictly for visual identification?
Yes, and you would want to release these parts with those hidden. This is just for the sake of the presentation.
You could also write a script to go through
distances between everything.
Yeah, I should have mentioned that. So all these elements, you should publish these elements to where you can consume them down the road.
And then just keep in with that, assuming you can either individually archive them or as a group.
Sure, I mean, when you're going to review, you would do it. Because when you start dealing with bigger assemblies and you start to zoom out, it kind of gets a little hairy when you have all this stuff visible.
Right.
So yeah, just for the presentation, everything is shown, but those surface references would be, as well as the access system, center line, those would all be hidden. All right, so yeah, so just selection, you can multi-select, do all of that and get those parts as you want them. So filters, this is really cool. Don't look at the smiley face just yet, forget about it. So you can see it in the little green box. Now the parts are resolved. We've got the little green balloon next to them. So we look at the top left, we've got a white balloon, green balloon, yellow balloon, red balloon. So those are filters in the system. So you can actually select the white balloon and it will remove all of your unresolved parts from your trees. So it'll make it much easier to navigate when you're only looking at the parts that you have resolved. Of course, the green one is resolved items. The yellow one is you have a resolved part, but it is not the latest version. We're going to go over that in a second. And of course, the red balloon is parts that have failed resolution. So it makes it easy for you to kind of go through and find them. But let's imagine we're looking at AN3 through AN20, where we've got almost 20,000 individual line items. We don't want to go hunt and peck for the specific ones that we want to do. The filters are actually pretty robust in the part families. So you can see we have a filter icon in the tree. Do not let that fool you. You can't do anything from the tree on that side. And we'll get more into that here in a little bit. But you can hit the new filter icon up in the top right, and you get this dialog box that pops up. And you can start to select. You can see these are all attributes that come out of our design table. So if you're looking for a specific thread size, a specific material, specific length, you can build up that filter and it will automatically create you that list of data that you're looking for. But this one's not working for some reason. This does not make me happy. It looks like I've made another mistake. It's giving this error that I've got some kind of a syntax error by a parameter called dash number. Well, that dash number was different than this dash number. So I put a period at the end of that. Anyone who's worked with querying or EKL, that period has a lot of meanings in the behind the scenes things. You know, it could be part body dot color, part body dot activity. So it was kind of freaking out, and I wasn't able to do any filters. So to resolve parts, you have to release your master model design table. So to fix this, I'm going to go in and I made the decision, I'm going to revise my model and design table, I'm going to correct this parameter, and then we're going to move on with our lives so we can create filters. But my component family now is still at the previous revision of the master model design table. So we want to select this little upside down white bolt right here, which is apply new revision to generic model. It gives you this dialog box where it will show you the available revisions of your master model that you can choose from. So we want to go to Rev B of this, and we're going to go ahead and say that the model was modified, and we are going to create new revisions of the existing parts. So there's a couple different options here. We'll go through those a little bit in the future, but CATIA is very, very specific. If you have something that's modifying your tree structure, especially if it's a parameter that goes down and feeds your geometry, you really need to revise your model and your design table. So that's what we did here, and we made our selections. So once we hit OK, what's going to happen is we're going to have to re-resolve the existing parts. So when we get to our new revisions, once everything has been re-resolved, it actually structures the new data in a pretty cool way. So what we see in the tree over here is the green bubble reflects the latest revision, and when we expand the tree, it shows the previous revisions underneath it on both sides of the tree. So as you revise, or if you continue to revise over time, you will have that history of all those models within your component family. So when we go back to our filters, we go ahead and we create our new filter. Okay, we're going to look for 1032 fasteners with a material code of S or carbon steel. So once we save that filter, and you can see the syntax for the filter pops up in the box there. We can actually see now that that filter populates in the tree underneath our filters bucket. And when we select that filter, it populates everything up on top, and it will filter all of our available configurations to the objects that meet that criteria. So in this case, we have 21 fasteners that met that criteria. So if we go through the process again of test and resolve family items, we can select the filter selection, pull the filter from the tree, and we can resolve just the items that are in that filter. Oh man, so much more. Okay, so but anyway, you can add additional filters as we go. So, and I was worried I was going to get this done too fast. So another option. So let's say you have a new revision of your industry standard that comes out, and they change the name to Jake's Make Screws instead of Screws Machine Flat. So there's no effect to your parts whatsoever, but this is something you want to get into your data. So if we go back into our, we revise our master model and design table, we update our specification name, re-release it. When we bring in the latest revision, we have an option to say that only the design table was modified, and we want to overwrite previously generated items. So if you have a design table change that has no effect on your model, or if you're adding additional configurations to your design table, or you're removing additional items from your design table, you can use this function. So how it works, like I mentioned earlier, when you go ahead and you accept that newer revision, you get the little yellow bubble that tells you you have to re-revise. I should have shown this slide earlier, my apologies. So when we go through and we re-resolve the released parts, we will see that the attributes overwrite the previous released, and all of our unresolved parts in our design table now reflect the latest parameter. So here's kind of an example of that. So the first part we resolved off of our design table at Rev A, but then we had that parameter that we created to get rid of the dot, which generated a Rev B. So between Rev A and Rev B, we didn't change the name of our specification, but when we went to Rev C, you can see that it overwrote the Rev B CAD to bring in the updated design table information. This is awesome because it's going to prevent a lot of unnecessary churn. You can make sure your data has the latest information. The but, though, is you have to have administrative privileges to do this. Not everybody's going to have that, so your results may vary. So again, we've got all of this put together. How do we get people to use it? So I've created a very simple catalog here. And what we're going to do is we are going to take the parts that we want that we have approved for use in production, and we are going to merge them into our design catalog. So this icon over here, which is the component management function, again, we have the option where we can add everything to the catalog, all, or we can use the filters. So depending on which ones you want to do, it's the same process as we've shown before. So to add to the catalog, we hit the folder button and we find the catalog we want to add to. And when we expand the catalog, we can actually pick the sub folder that we want to add the data into. And once we hit OK, that's when the magic starts to happen. So when we have a new product or an existing product open in our section, and we want to start adding fasteners, we open up our catalog, and you can see now that all of the released components that we had that we added are in this. So we have the 21 fasteners from our filter that we resolved, as well as the initial one. So everything is there. So that's still a lot of information to sift through. If you resolve an entire part family, you're going to have even more that you have to sift through. So we do have filter options where you can do very similar to what we've shown in the component family to narrow down the specific attributes that you're looking for. Of course, in this thing, we're looking for a specific length. You hit the plus sign, and that adds that as a level of filtration. But then you can build upon that, where you can have multiple levels where we have length here, and we want to add a material, specific material. If we have in that folder multiple different part families of countersunk bolts, you can narrow it down based on the specification. To ultimately get down to where we have the part that you want to instantiate. And you now have from initial design all the way to end user consuming your bolts, have a controlled means from cradle to grave of what fasteners your team is using.
Items.
Yeah. So I'm almost done. So